Hello, grade 11s. In today's lesson, we're going to be looking at electrostatics and we are doing practice problems. So without any further ado, let's just get right down to the lesson. So here we are given question 8. It says, two small identical metal spheres on insulated stands carry charges of positive 4.2 times 10 to the power of negative 9 coulombs and negative 6.8 times 10 to the power of negative 9 coulombs respectively. So as indicated in the diagram, we can see that. And then they say they are placed at a distance of 0.3 meter apart. So all that is evident in our diagram there. Then 8.1 says state Coulomb's law in words. So this is how you are supposed to state Coulomb's law. Coulomb's law states that the net electrostatic force is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. So that's how you are expected to define Coulomb's law according to your CAPS document. Then 8.2 says calculate the magnitude of the electrostatic force that the one charge exerts on the other. So what are we looking for here? We are looking for the net electrostatic force. Now we know the formula to calculate that one is the Coulomb's law formula, which goes F is equals to K Q1 and Q2 over R squared, right? So that's how we have our formula. Now we know substituting into our formula here, our K is 9 times 10 to the exponent of 9. Then what is our Q there? We have 4.2. So 4.2 times 10 to the exponent of negative 9. And then here, what is our Q2? The charge, we have 6.8 times 10 to the power of negative 9. Note that I'm not substituting a negative here. So for the grade 11 formulas, we are not substituting that negative. Remember that negative and positive only tells us that the two spheres will attract, right? Because they are unlike charges. So now we have that. So punching all this in the calculator, we have 9 times 10 to the power of 9, and then all that, it gives us 2.86 times 10 to the exponent of negative 9. And then remember, this is a force, it's an electrostatic force, so it should be given in newtons. That's how you have it, right? Now let's check 8.3. So we are given a statement above there. It says the two spheres are allowed to touch and are then returned to their original positions, right? So now we have a case whereby these two spheres are now allowed to touch. So we can see that when they're left out to touch, they will obviously attract each other because initially they have unlike charges, right? So this one is a positive and that one is a negative. So they are bound to attract. Remember, unlike charges attract. But now after they touch and then return to their original position, we know that after the spheres touch, they will then share electrons. And finally, the Q nu will now be equal in both these charges, right? So this is what we are told to calculate in 8.3. It says calculate the new charge Q on each sphere, right? So we know after they touch, they must have the same charge, right? The new charge must be the same. Now let's go with that one. So we know our formula from grade 10, which is Q nu is equals to Q1 plus Q2 over 2. So this is the formula we use to calculate Q nu. So our Q1 being 4.2 times 10 to the exponent of negative 9, then plus, remember this is a grade 10 formula, so we substitute in the negative, then negative 6.8 times 10 to the exponent of negative 9. then all that over 2, right? Then having to punch all this in your calculator, what is it that you will have? It's negative 1.30 times 10 to the exponent of negative 9 coulombs, right? And that's how we have it. So that's the new charge. Now, what does it mean? It means that this charge here will now have a magnitude of negative 1.30 times 10 to the power of negative 9 coulombs, and also this charge here will have that this one new, right? So after they come into contact and then separate, they will both now have that's right. So now Q is 1.30 times 10 to the exponent of negative 9, and also this charge, hence you can see that both Q to indicate that they now have the same charge, right? So they will now have the same magnitude of charge. Now this is what will happen since they now have the same magnitude of charge, and also we can see this is the same type of charge. So what will happen? They will then separate. They will then separate as a result of having those like charges. Then for 8.4 it says draw the electric field pattern between the two charges, or between the two charge spheres. So these spheres now, after they have came together and then separated, we must now draw the electric field. Note that we are not drawing the electric field of this one. We are drawing after they are made to come into contact. So that means now we are drawing for a negative and a negative. That's a repulsion, right? So the way we are supposed to draw that one, we now have negative here and a negative there. But we know like charges, they do what? They repel. So indicating our field lines. So you don't want to have so many field lines, because you don't want to risk your field lines touching each other. So you want to have the minimal number of field lines. Now we know what is happening with this. The charges will be inward. Since it's a negative, charges must be inward. So forgive my drawing, it is not that nice. Then charges will be going inward. So you get the idea here. The idea is that charges need to go inward because it is negatively charged. Now here the charges must not touch, because remember this is repulsion. This is repulsion. So your charges, your spheres must not touch, they repel each other. Okay, now let's look at the last question, which is 8.5. It says now calculate the magnitude of the net electric field at point P situated at 0.1 meter to the left of the spheres as shown in the diagram above. Now you will note that every time we are calculating the net electric field, we have to calculate in reference to the positive point charge. So the positive point charge is always indicated by that P most of the time, right? So now that means we are calculating the the electric field of P due to this first sphere here, and then we are also calculating the electric field at P due to the second sphere here. So everything that we are calculating is in reference to P here. Now you will remember that we now have the Q new for each of the spheres, so which is 1.30 times 10 to the exponent of negative 9. So each sphere possesses this magnitude of charge, right? So in order to calculate the magnitude of the net electric field at point P, we need to do what? This is how we have it. For 8.5, we now have so calculating the electric field. For the first one, we have E is equals to KQ over R squared. Now what is our K? Our K is 9 times 10 to the exponent of 9, right? And then our Q there, remember the new charge for Q is now 1.30 times 10 to the exponent of negative 9. So you do not make the mistake of substituting that first value above there. Remember we say the spheres have now touched and then have shared electrons. Then this is 0.1, the distance, and then punching that in your calculator, you have 1170 Newton per Coulomb. Now, if you did it in scientific form, if your calculator is in scientific form, you'd have something like 1.17 times 10 to the exponent of 3 Newton per Coulomb. Note that these values are the same values, right? This is for someone who has his calculator in normal form, and this is for the one who has his calculator or her calculator in scientific form. So do not be confused as to how we have different answers, like they're the same. Then E is equals to KQ over R squared. So now we are trying to calculate for the second one. So again, we have 9 times 10 to the exponent of 9. And then what is our Q? Still the same values, 1.30 times 10 to the exponent of -9. And then what is the distance now? To see the distance between the second Q and P, you will note that the distance in between them is 0.4, and then you square that. Now let's bring out the value for this one. You have, punching that in your calculator, you have 73.125 ton if your calculator is on normal, but then if your calculator is on scientific, you have 7.3125 times 10 to the exponent of 1, and then Newton per Coulomb. Here also Newton per Coulomb, right? Then let's look at the directions. So since we say P is a positive point charge, and then we have deduced that our charges are negative, we know what will be happening here is that now these charges will do what? They will attract, right? So remember that one is positive, and the positive point charge is positive, and the charges are negative. So where will your point charge go as a result of these charges? Your point charge must be attracted to the right. Remember, this is in reference to the point charge. So the point charge, due to that negative sphere, will now be attracted to the right, and even this one will now be attracted. Even due to this one, it will be attracted to the right. So that's your direction. But now we are not done. We are asked to calculate the E net. So now to calculate the E net, you must consider that if they are going in the same direction, they will add up. So we have E1 plus E2. The E1 being the one that we calculated first, and the E2 being the one that we calculated second. Then remember, we have 1170 plus 73.125, and that will give us 1243.125 ton per Coulomb. To which direction? Right. Then if you still have your calculator in scientific, you have E1 plus E2, and then remember, what is the values that we got? It's 1.17 times 10 to the exponent of 3 plus that one gave us 7.3125 times 10 to the exponent of 1. So adding this, you have, so if you round off to 2 decimal places, you have 1.24 times 10 to the exponent of 3 ton per Coulomb to the right. So your answers can either be that in normal form or this in scientific form. So both these approaches are correct. Nice. Okay, so we have question 3. It says A sphere Q1 with a charge of negative 2.5 microcoulomb. So let's highlight that one. We have microcoulomb is placed 1 meter away from a second sphere Q2 with a charge of positive 6 microcoulomb. The spheres lie along a straight line as shown in the diagram below. Point P is located at a distance of 0.3 meter to the left of sphere Q1. The diagram is not drawn to scale. So now we can see that this all indicates the information that we have above here. So even if it is not drawn to scale, but then all the information that was spoken about is indicated here. We can see the charges, and then we can see the distance between Q1 and Q2 is that 1 meter. The distance between Q1 and the point charge P is 0.3 meter, meaning the distance between Q2 and the point charge is now that 1 meter plus 0.3, which will give us a total of 1.3 meter. So okay, that's the information that we can extract from this diagram here. Then 3.1 says define the term electric field at a point in width. How do we define that one? Say electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So this is how you are expected to define electric field at a point according to your CAPS document. Make sure you memorize and remember it. Then 3.2 says draw the resultant electric field pattern for the two spheres. But then the two spheres, we can see that they are oppositely charged, right? They are unlike charges. So this one is negative and this one is positive. Now we know what happens when we have unlike charges. We know that we will experience a force of attraction, right? So now having to draw the electric field pattern for that, we have this side here, we have a negative, and that side we have a positive. And then we know this is attraction. So remember, you don't want to draw many field lines because you don't want your field lines touching, right? So extend that one, then have it like that. So you don't want to risk having your field lines touching. So you draw as little as possible just to indicate what is going on. So maybe we can add one. In fact, let's not add anything. Okay, so let's fix here. So you want to make sure you don't have a touching the lines. So we write this one, connect it here. Then since this is a negative, we expect our charges to be going inward to the negative. So our arrows are going inward into the sphere, but then for the positive, they are going outward. So the flow of charges is outward in the positive sphere and then inward in the negative sphere. So this is how you have it. That's your electric field pattern. Nice. Now let's look at 3.3. It says calculate the net electric field at point P due to the two charges, due to the two charge spheres Q1 and Q2. Now you will remember that we said when we are calculating the net electric field, everything is in reference to this point charge. So that means we'll be looking at the electric field due to Q1 first, and then looking at the electric field due to Q2. So the electric field at P due to Q1 and the electric field at P due to Q2. Everything is in reference to this positive point charge. Now let's go. So for E1, we have K Q1 over R squared, which now this will be the electric field at P due to the charge Q1. Then K is 9 times 10 to the exponent of 9. And then what's the value for Q1? We have 2.5 times 10 to the exponent of negative 6. Remember, macro Coulomb, when we convert it to Coulomb, it becomes times 10 to the power of negative 6 coulombs, right? And then over, what is the distance now between that positive point charge and Q1? We can see from the diagram is 0.3 and then square. If you punch that in your calculator, you have 250,000 ton per coulomb, right? If you have this in scientific form, that's 2.5 times 10 to the exponent of 5 Newton per coulomb. And where is it going now? It is going to the right, so we can see a force of attraction between the point charge and Q1. So the point charge will be going to the right as a result of that. Now let's do E2. For E2, we have K Q2 over R squared. Now our K is still 9 times 10 to the exponent of 9. That's a constant. And what's the value for Q2? That's 6 times 10 to the exponent of negative 6. Still macro Coulomb. And then the distance in between P and Q2 is 1.3, right? So it's 1.3. Remember, it's that 1 plus 0.3. And then what do we have? Punching that in your calculator, you have 31,952.66 Newton per Coulomb, rounded off to 2 decimal places. Now, if you have it in scientific form, that's 3.1953 times 10 to the exponent of 4 Newton per Coulomb. So in scientific form, you don't want to round off to 2 decimal places as yet, because remember, in scientific form, they're working with those big numbers. Then to calculate the E net now, so this one is going to which direction? This one will be going to the left, because remember, the point charge is positive and also Q2 is positive. So we'll experience a repulsion force due to that, and then as a result of that, the point charge will be going to the left because it will be repelled. Then E net is equals to E1 plus 2. So indicating our directions, this is E2, right? And then this is E1, right? Then what is the value for E1? We have 250,000, and then plus our E2, remember, is now a negative, right? So it's negative 31952.66, and then having to punch that in a calculator, you have 218,047.34 ton per coulomb. So since now it comes out as a positive, we know the direction is right, because let's indicate we took right as positive, right? So since it comes out as a positive, that means it's going to the right. If you have it in scientific form, your answer should be something like 2.18 times 10 to the exponent of 5 ton per coulomb. Then still it's going where? To the right. So those are your values. All the best, guys. Keep on practicing, and then subscribe to the channel, like and comment below. Ra!